Okay, we're going to continue our talk about ionic compounds, and we're going to finish off by talking about acids and bases. And this kind of, again, continues similar to our hydrogen bonding to our polyatomics and diatomics. This follows the same kind of suit. So you probably have already heard about and kind of know what an acid does. They are corrosive, can potentially cause harm, but not all acids are going to be corrosive and dangerous because you can eat some of them, which we'll talk about later in the course. But for now, what we're really going to do is we're going to talk about how we can identify an acid by looking at a formula. And if we see a formula, how can we name it or know it to be an acid? And that's what we're going to do here. Now, acids are compounds that ionize or come apart in water, and they release hydrogen ions. Thus, the positive ion in acids is always the hydrogen ion, which is H plus. Okay. Now, the key thing about this is that an acid is not technically an acid until it's placed in water. Okay. So, in order to be an acid, they have to be dissolved in water. Okay. So, we'll talk about that a little bit later and how that we're going to represent that. Okay. Now, acids in their pure form are simply just molecules, and we'll look at some of them down here. However, they are named according to our ionic rules. So technically, they are molecules with covalent bonds, but when you put them in water, their bonds break, and then the electrons are transferred between the two things in the bonds, and you end up with ionic components from the acid, which is kind of neat. When an acid is dissolved in water, the name is changed to reflect that it is an acid, and we'll talk about that. So kind of what's interesting about this is that when it's not in water, you name it differently than when it is in water. And maybe we'll briefly look at that a little bit in just a second. Okay. Now, there's two different types of acids we're going to discuss here. The first type of acid is ones that do not contain oxygen. And what they're characteristically going to have at the end of their name or part of their name is ic acid. Okay. So ones that don't have oxygen are going to have be something ic and then acid. Okay. So for instance, if you took an acid that has fluorine in it and is again attached to a hydrogen, right? So this one here, we know that this is going to be not having oxygens in it. So we're going to use this formula here of ic acid. Okay? So if you had HF and you put it in water, and that's what this represents here. This represents dissolved in water. This AQ, which is aqueous. Okay, so that's aqueous, and that means that the acid or the molecule that is acting as an acid has dissolved in water. Okay, so if I have HF and I throw it in some water, we're going to change the name because technically it would be hydrogen fluoride, right? Hydrogen fluoride. That's what the non-water name would be. But if we put it over to this, or I guess a hydrogen monofluoride, I guess, but hydrogen fluoride is fine. But if you throw it into the water, it becomes hydrofluoric acid. So I forgot about this part up here, is that there's also going to be a hydro. It's not at the end though, right? It's at the beginning, so it's a prefix. So hydroic acid. So hydrofluoric and then acid. And those are the parts that we mentioned before, right? So there's the hydro, there's the ic, and then the acid. And this is whatever the element is in the middle there. In this case, it's fluorine hydrofluoric acid. If it was sulfur, it would be hydrosulfur, so sulfuric acid. But again, it's the same change. The only difference is that the element has changed in there as well. Okay. Now you notice that this one is a polyatomic, but there's no oxygens in it. So you use the same system, hydrocyanic, because that's our cyanide polyatomic, cyanic acid. Same thing, just because there's no oxygens, it's hydro, ic, and then acid. Okay. And remember, and then for any things to be treated as an acid, they first have to be thrown into the water, and then the name changes. Okay. Right, that was hydrogen cyanide, sulfur, hydrogen sulfide, just like the hydrogen fluoride, and then you change to reflect that it's in an acid, and so on. Okay. So if you had HI or high, this is iodine, but we know that it has an H with it, right? So it's going to be H's with iodine. So it would be hydrogen iodide But when I throw it into the water and become an acid, it's going to be hydroiodic acid. There we go. Hydroic acid. Oh, there we go. Hydroiodic acid. Okay. And then the same thing applies for B. Okay. So HBr. So this would be hydrogen bromide. But when I throw it into the water, we change this to reflect that it's an acid. So it would be bromic acid. And then there you go. So hydrobromic acid. Okay. And it's pretty straightforward. So as long as there's no oxygens in here, you use hydroic acid. Now, there are clearly, since we talked about ones with no oxygen, there are clearly ones that do have oxygen, and we call those oxoacids or oxyacids because in addition to having hydrogens, they also have a polyatomic that has oxygen in them. So this is kind of like we're going to use these rules for the things we saw for the polyatomics that have oxygen in them, like carbonates, phosphates, sulfates, chlorates, and our nitrates. So all of these are going to be part of this whole oxoacid naming system. So the naming rules are the same as kind of with oxygen, but since they have that polyatomic, we're going to have to consider how many oxygens they have, right, in them. So remember, carbonates, percarbonates, carbonites, and so on, that's all going to come into play as well. All right, so here's our table. It looks a lot like our polyatomic one, but this is only for the oxoacids or oxyacids, the ones that have a polyatomic that have oxygen in it. Okay? So the root up here is just the name of your polyatomic. Okay, that's what this is representing here. Okay. So this is your regular polyatomic name. Okay. And the normal one, the basic one, is just your 8, right? So if it was carbonate, it would just be, this is carbonate. Okay. And this would be carbonite, hypocarbonite, and percarbonate. Okay. Now, when they're thrown in water, so when dissolved in water, the name is going to change and reflect the fact that it's an acid. So we're going to change the base name into the acid name. And really the only difference is the ending. The beginnings are the same. So the hypo and hypo are the same, and the per and the per are the same. The only difference is the ending. Okay? So if we take chlorate, for example, so here's chlorate over here. This is just the basic regular version of chlorate. If I have perchlorate, which means there's one more one more oxygen in there, then I change it simply. This name stays the same, except I put ic acid on the end, and that's it. Okay. So the only thing that really changes is the ending in all of these. Nothing really else changes. Okay. So this would be ic acid. Okay. The regular one would be, instead of chlorate, it would be chloric acid. Us is one less. So this is where it's slightly different, and then the ending is, it's still ite, chlorate, but the ite is now chlorus. The eights become ix, and the ites become us's. So here's ite, and that's us. And that'll just be something that you get used to. So the regular version that have eights as their ending, they turn into ic acids, and the ones that have ites, they become us acids. I should have probably used a different color for that. So let me just do these in green. These are the us acids because those are ites. And the eights become the ix. Eights become ix and ites become us's. So if you had to take this molecule here, HNO3, okay, I'm going to first look at my polyatomic, so it's nitrate. It's the regular version of having 3, so I know that it's an 8. So then I just simply change the 8 into ic acid. So this would be nitric acid. Okay, so remember, it's an ic acid because it was a nitrate. So 8s become X. Okay? If we look at H3PO2, okay, this is 2 less than so this is a phosphate, but it's 2 less, so it's actually hypophosphite. And because I have an ite, it's going to become an us. So this is going to be a hypophos acid. I guess it's hypophosphorus. Hypophosphorus acid. Hypophosphorus acid. Okay, so that's an us acid. Ites become us's. All right, so you can look at C here. So this is H2SO3. So this is SO3, which is sulfite. Okay, so we know it's an ite. And it's 1 less. So we know there's no hypo because that was 2 lesses. That's why it's got the hypo. This is 1 less, and it's an ite. So I know that this is going to be sulfurous acid because ites become us's. There you go. So the bases are pretty straightforward. There's no real naming rules for bases. That will be changed a little bit in the future, maybe grade 11 or 12 chemistry, but for now, we're simply going to have there's no new system for bases. All the bases in this course maybe that's not true when we get to S and bases, but for the point being now, bases always have hydroxide in them. Okay? So bases are compounds that have hydroxide ion in them. So you will identify a base by identifying a hydroxide polyatomic in its formula or in its name. And that's it. But there's no different naming system. You just name it according to the polyatomic rules. So for instance, if you had KOH or CO, you would just say or name or normal things. You name the positive ion, you name the negative ion. There's no changing in the amount of oxygens here. It's not one of our oxo acids, or it's not one of our polyatomics that varies in oxygens. It's always this one because it was not an 8, right? So then you just name this one as potassium hydroxide. And it's the hydroxide that tells you that it's a base. Okay? So if you had B here, which is LiO, right? It's just lithium hydroxide. And that's it. And I know it's a base because I have a hydroxide in the name, or it's because I have OH in the formula. And then C here, Mago, is the same thing. It's just magnesium hydroxide. And that's it. Now you might get, so let's say for instance you had ammonium, NH4OH. And again, the same thing applies, right? It's still just an OH. So it's ammonium hydroxide in that case. Even though it's 2 polyatomics and not just a metal. So you don't have to have metals as your positive ion. Okay? The negative ion basis is always the hydroxide ion. Naming formula writing is the same as your other ionic compounds. You already learned the rules. We're just now identifying these things as being bases. The term alkali is used to refer to a base that is soluble in water. And these, in order to be bases, would also have to be dissolved in water, just like the acids. So if they're not dissolved in water, then they don't act as bases. So they're not corrosive and stuff like that. So to be fully functioning in chemistry like a base, they have to be in water. Outside of water, they're not.